Oh yeah, before we get started. No, actually I'll do that at the beginning of part 14. So we talked about equilibrium vapor pressures. That's hard to say. Equilibrium vapor pressures, right? There are certain situations where the equilibrium vapor pressure will be lowered if it has what we call some sort of contaminant or some sort of solute in it, some sort of thing messing it up. Equilibrium vapor pressure lowering. Now, in order to kind of talk about the lowering of an equilibrium vapor pressure, some sort of contaminant, that actually, as it turns out, is a colligative property of matter. We're used to seeing things that its effect increases with, or I guess we're used to seeing things that it depends on what the interferer is. The way colligative properties work, it doesn't matter who's interfering, it just matters the amount they're present in. Colligative properties does not matter on the identity of the solute, the thing doing the interfering. It just matters in how much there is. That's a colligative property. So I mentioned interference. So vapor pressure lowering happens because something's there running interference. Makes sense to me. We're going to see some videos. The thing that's running interference for the solvent, which is there in a large amount, the solute, the thing that's been added to run interference, is generally non-volatile. Okay? So we generally add something that's not going to evaporate to something that usually does evaporate, and it lowers its equilibrium vapor pressure. So here's a video to kind of show you what that looks like. I like things in certain equilibrium vapor pressure at that temperature. If we add a solute, some sort of solute, now colligative property doesn't care what that solute is. That's these foreign blue particles. It just matters that they're present. So, for instance, have you ever heard that, I think we talked about the water boils, how does this work? Well, water will boil at a lower temperature if you're at upper elevations. Stay at the same elevation and add salt to your water, and it's going to boil at a higher temperature. You add salt to your water, you have to pump it with more energy in order to get it to boil. Water boils at a higher temperature if you add salt to it.
How should the salt in with your noodles keep them from sticking together?
I don't know. It depends on, the chemistry of cooking is just amazing. I don't know much about it, but it depends on if you want it to boil at a higher temperature when you add salt. I think the sticking is like butter. It wants some sort of lubricant. I don't know how that works or what. But yes, the equilibrium pressure lowering. So we talked about physical or pressure, temperature, phase diagrams. That's exactly what we've got here. So here we have our solid sector, here we have our liquid sector, here we have our gas sector. But can you see actually two Y's there? Okay. One Y, I think this is right. Oops. Okay. I think that's what I'm going to do. So this guy, this is the original. And when I say original, it's like your water that nothing's been added to. This second Y down here is your solution. When I say solution, that means you've added a solute to the solvent. So boiling point elevation, that's exactly what we described when we add sodium chloride, when we add salt to our water. Our boiling point temperature will become elevated. Delta T, B as in boiling, that's exactly what's being shown there. So the way this works is if we were to pick out a pressure, well actually 1 atmosphere, remember by definition something boils when its equilibrium vapor pressure is equal to 1 atmosphere. You can see here where this is where it boils in its pure state and this is where it boils if you have added a solute to it. See how that works? Because we have the solid purple line, the pure stuff, and then we have the dotted purple line, which is the solution that the solute's been added to it. That's your boiling point elevation right there. Now we're going to talk about the phenomenon of freezing to which a solute has been added. So here's the deal. what happens when we put salt on our sidewalks? We're hoping to melt the solid ice. We're hoping to actually lower the temperature at which ice freezes, freezing point depression. Another colligative property, and we're going to see a video to how that works. But what that would do is kind of over here. Notice, now remember, this is the original pure stuff, and this one is the solution. And those are freezing point temperatures, where it transitions between the solid and the liquid on the pressure temperature phase diagram. So notice that the solution has a lower freezing point, and the one that's a pure stuff has a higher freezing point. Yeah, I'm saying it right. Okay. So we call this boiling point elevation and freezing point depression. And this actually is just a part of the Y. Okay, this is your equilibrium vapor pressure curves, where the red is the pure stuff and the blue is the solution. So up here, we can see our boiling point elevation right there. And then here, actually, if we take it at the same temperature, notice we can see the effect of, I called it interference a minute ago, we can see the equilibrium vapor pressure lowering, because remember the red is the pure and the blue is the one that's had some solute added to it. That's your equilibrium vapor pressure lowering at 60 degrees. But you can pick any temperature and see that effect. So I've been talking about the original or the initial. What we do with regard to keeping track of things is we give it the little, I call it a knot, like K-N-O-T. I think we've used this before in Chem 1. So I'll call that P-knot. P-knot. What does that mean? It means the original. It means the pure stuff. And then we'll call just regular P, okay, one that has had a solute added to it. Okay, so this is the solution that has the solvent and a solute added to it, okay? So we've talked about deltas before, like delta H, delta H's, delta this, delta that, delta T's. And deltas are always final minus initial, always. Final minus initial. Because a lot of times there gives the sign, like if it's negative or positive, is a deal. So if we make our final the solution, okay, so that's the impure stuff. And our initial, that's going to be our P naught, basically, what we start with, the pure stuff. That's how we look at this. So the initial conditions are the pure solvent, and that's going to be your P naught. And the final is going to be the pressure of your solvent, to which a solution, to which a solute has been added. Makes sense, you accept that. So here in a minute, when we talk about the change in pressure of the solvent, you know what it's going to look like. So it's final minus initial. So it's going to be our P of the solvent minus the P naught of the solvent. Final minus initial. There it is on the next slide. Got ahead of myself. But I feel like I tried to make a big deal out of it because it's a subtle thing, but it makes a difference when you're looking at working the problem. Okay, so equilibrium vapor pressure lowering. A colligative property depends only upon amount, not what you put in there. So this is kind of interesting. So I use salt, the term salt. Actually, in chemistry, it's not just sodium chloride, is it? Any ionic compound is a salt. So a lot of times when you buy stuff for your, to melt the ice on your sidewalk, it's like calcium chloride or magnesium something, okay? So it depends only upon, oh, wait a minute. Okay. So the equilibrium vapor pressure that's going to be above your liquid is actually going to be a function of how much solvent particles you have. So we did this proportionality symbol before, where we can say that the pressure of your solvent above your vapor solvent above your liquid solvent is going to be, is proportional to, didn't we talk about mole fraction? When we talked about earlier about concentration, so your X is mole fraction, the mole fraction of the solvent that's there. Makes sense. We learned when we used a proportionality constant to come to develop the ideal gas law equation, we can take the proportionality constant, we learned about proportionalities, that we can remove the proportionality symbol if we introduce a constant. We can make it equal. So the equilibrium pressure of the solvent is equal to some constant K times the mole fraction of the solvent. Makes sense. And we can actually come up with a value for K. And it looks like this. What if the solvent that you're dealing with is pure? If the solvent that you're dealing with is pure, that means its mole fraction is 1. So if its mole fraction is 1, if it's pure stuff, then does this make sense that that K actually is going to be your P naught? So the way it works out is this. Kind of prove to you why this is with just that one little bit of evidence. For any pure substance or mixture, it's probably going to be a volatile solvent to which a little bit of non-volatile solute has been added. The equilibrium pressure of the solvent is going to be equal to the mole fraction of the solvent times the equilibrium pressure that the solvent would have if it was pure. Thus, the P naught is important. I made a big deal on it. This is your pure stuff. Okay, and this is your mixture or solution. Makes sense. Oh, here's my little note. Okay, so the mole fraction of your solvent is going to get less and less as you add solute to it. And then if that's the case, then your equilibrium vapor pressure will go down of your solution. And that's called Raoult's law. Let's see if this link works for me. It did work for me. Now skip to 14, and let's kind of apply that to that colligative property of adding a non-volatile solute to solvent, and we'll see the boiling point rise, and we'll see the freezing point get lower. So again, the solid purple, that is your pure stuff. And the kind of the dotted purple lines there, that is actually how the solution will behave with regard to its transition from a solid to a liquid and its transition from a liquid to a gas, or from a gas to a liquid and from a liquid to a solid. Boiling point elevation, freezing point depression kind of rolls off your tongue. So for, boiling point elevation would be right here. We're going to use delta as in change in the temperature of the boiling point. So delta TBP is the change in boiling point. It's going to be an elevation. Over here, this is going to be the change in the freezing point temperature that we can see up here. And this will always be a depression. Okay. Boiling point elevation, freezing point depression. Colligative properties of the solute that you're adding. Again, we just saw this a minute ago. This is isolating just that one part of the pressure temperature phase diagram between liquid and vapor. This is what we would call an equilibrium vapor pressure curve. The red line is the pure stuff, and the blue line is the volatile solvent to which a non-volatile solute has been added. So we can look here at the boiling point elevation. We're actually going to kick out some numbers for these things. In this case, the solvent was benzene. We add a solute to it. It has a new boiling point temperature. If you were to subtract these two temperatures, the boiling point elevation is 5.1 here. The equilibrium vapor pressure lowering, just picking here, 60 degrees. Okay, how far does it go down? It's looking like 54 millimeters of mercury. So this is showing you the solution is the thing of interest. See, this one confuses me. The thing of interest is that pink material. So here it's actually in its pure state, and this little globule here is where it's been able to, an impurity has been added. So here we can see it's solidified, and here in its solutions, to which a solute's been added, it hasn't solidified yet. Okay, so we kind of talked about the dissolving process. This is showing you the dissolving process now. Sorry, it's not showing the dissolving process. It's showing you the equilibrium between solid and liquid. So I'm going to put a little S there, my pile of black dots, and I'm going to put solid liquid. Okay, so that's not dissolving. That's the same stuff that is melting. Okay, so melting going this way, freezing going this way. So again, we talked about running interference. What if we put something up here to kind of, now we don't have something pure that's between its liquid and solid state. Now we have introduced an impurity, and that actually adds interference for your liquid to go ahead and solidify. So the degree of solidification is less over here. So this would be freezing point depression. To reach the same equilibrium, we're going to have to lower the temperature in order to get the amount of freezing going on that we had over here because of the interference. All right, so Raoult's law, right? The equilibrium vapor pressure of the solvent to which a solute has been added is equal to the mole fraction of the solvent times the equilibrium vapor pressure of the solvent if it was pure. Well, if we go ahead and recognize it's a binary meaning two, just make two things in our solution. We have the solvent in greater amount, solute lesser amount. The mole fraction of both of them should add it to be equal to 1. We can rearrange this, and we can solve for the mole fraction of the solvent is 1 minus the mole fraction of the solute, assuming there's only one solute. Well, we can substitute this quantity back in for the mole fraction of solvent, and it looks like this. Okay, so, and now next line, what you're going to see is we're going to distribute this mole fraction of the solvent through this quantity right here. Sorry, mole fraction. I'll say it right. Oh, we're going to distribute this equilibrium vapor pressure of the pure solvent in through 1 minus the mole fraction of the solute, final answer. And it looks like this. Well, now we can kind of rearrange them and come up with the delta P. Delta P is what? P minus P naught. Okay. So P minus P naught and is equal to negative X, the mole fraction of the solutes times the mole fraction of solvent. I will complain right here. I have nothing to fix it, but is it just me, or do those subscripts those words just drive me nuts? The mole fraction of the solute times equilibrium pressure of the solvent is pure state. Well, anyway, maybe it's just me. So that quantity over there on the left, of course, is delta P. So we end up with something like this. And as it turns out, this change in equilibrium vapor pressure that we kind of saw at 60 degrees a little bit ago for our benzene, okay, that delta P is equal to negative mole fraction of the solute times the equilibrium pressure of the solvent in its pure state. That's just another form of Raoult's law. I like the name Raoult too. Well, we're getting close. We can actually take that a step farther and apply that specifically to the boiling point elevation and the freezing point depression. And now I will double check, because did I tell you guys you got to have that I will give you an equation sheet? I will double check before even tomorrow. I'll see, because I think Unit 1 I give you guys equation sheets. I think you need to know what to do with them. Okay, but so that delta TBP, the boiling point elevation, is equal to K, and I'm going to tell you that's that's the boiling point elevation constant. So K you have to look up on a table or figure it out some way. Now, what's the lowercase m? Molality. Yes, molality is your friend. So dragging you through all those solution concentrations to understand molality, you needed to know molality, which is moles of solute per kilogram of solvent, in order to solve these problems. So there's that one, and then there's this one. Okay. So what do the double bars mean? Absolute value of. Yep. So how depressed your freezing point temperature is going to be looks like this, where we're going to take the freezing point, constant, the freezing point constant for the solvent times the molality of the solute to get how much it's depressed. So our delta T's, whether it's delta TBP or delta TFP, are calculated this way. So what does the T and the T naught mean? What does the T naught mean? Pure stuff. Yep, T naught means it's pure stuff. T means the temperature at which it boils or freezes when it's in its mixture. So as this, we talked about boiling point elevation and freezing point depression, the delta T actually will be positive for your boiling point elevation, and it will be negative for your freezing point depression. Now, so over the years, as I've come to this subject, this is one of those subjects where there's different ways to handle the problems with regard to the sign, the convention of your freezing point depression. And so just bear with me, because we're going to take the absolute value of our delta T, which what? It's not negative, it's going to be positive. And it's all going to work out fine. So what do these look like? I'll show you how they look, and they're kind of fun, straightforward problems to work. So the KFP has to be specific for the solvent. See, I get my solutes and solvents mixed up. Right. But the KP is specific for the solvent, and the BP is specific for the solvent. They would be two different constants. Okay. So I'm going to show you some boiling point elevation constants and freezing point depression constants right here. So these would make, generally I could see us using these as solvents. You can use water as a solvent. We used benzene as a solvent a minute ago on that example for that figure. hydrogen acetate, chloroform as a solvent, nitrobenzene. And then you add a little bit of solute to it, okay, and it will elevate the boiling point or it will depress the freezing point according to its colligative property, depending to the molality of the solute that you added. So these are the boiling point elevation constants. Now, when you work these problems, and you'll see why this is, but you need the transition point. You need the transition temperature. These are transition temperatures. In this case, when it goes back and forth between a gas and a liquid, the boiling point temperatures. So the same substances, if you're working a freezing point depression problem, you need the freezing point depression constant right here. And these are the transition temperatures that for those solvents, potential solvents, the temperature at which they transition from a solid to a liquid or a liquid to a solid. So you need to know those to work the problem. Okay. So units of the boiling point elevation constant or the freezing point depression constant are going to be temperature. We're going to go with Celsius. So degrees Celsius per molal. Okay, degrees Celsius per molal. Now, molal, we said, was what? Mole of solute per kilogram of solvent. So we could actually unpack molal, and it would look like this. It would be mole of solute on the bottom, kilogram of solvent on the top. So that's another really valid unit for your boiling point elevation and your freezing point depression constants. And that's why it is. Okay, here's just another table. Add some other things in there. Some holdovers. Okay, some similars and a few different. But remember, we have the in this case boiling point over there on the right, freezing point. Second need for freezing point depression on the left. So this is where I kind of tell you, just be patient with me as I kind of transition. Remember a little bit ago, I said we're going to go with the absolute value of the freezing point depression is equal to your freezing point depression constant times the molality of your solute. Sometimes, though, just to warn you, sometimes, and I think I've done this throughout my 15 years, you can actually put a negative sign in front of that little equation to have it kind of come out positive. Sometimes the freezing point depression constants, your KFPs, will be negative. I'm just warning you. Okay, but we're kind of going with this last one. We're going to work with the magnitude, the absolute value of the freezing point depression. But you need to recognize, and again, it kind of rolls off the tip of your tongue, freezing point depression. The new temperature is going to be lower, okay, for freezing point. And boiling point, the new temperature is going to be higher. So just kind of keep all that in mind. So let's work a problem, and we'll pick on benzene. So in the last couple slides, for benzene, we know everything. We know its boiling point temperature, its boiling point elevation constant, its freezing point temperature, its freezing point depression constant. So what is the freezing point of a benzene solution that boils at this elevated temperature of 82.0 degrees Celsius? It's like a little riddle, okay? If we look back a few slides, we can see its boiling point temperature is elevated because the T naught to BP, the boiling point temperature of pure benzene, is 80.1 degrees Celsius. We're at 82.0. So yeah, you definitely have some solute added to it. And the freezing point depression is going to be lower. The freezing point temperature is going to have to be colder than 5.5 degrees Celsius. Okay, the boiling point elevation constant is 2.53 degrees Celsius per molal of solutes. And the freezing point depression constant is 5.12 degrees Celsius per molal. So the strategy here is basically to see how much use the elevation to knock out the molality of that secret solute that's doing the elevation, boiling point elevation. We need to know the molality. It's a colligative property. We don't need to know the identity. We only need the molality. Once you have the molality, we can go ahead and stick that into the freezing point depression equation, and we can find the depression. We apply the depression to what it freezes at under norm when it's in its pure state. So it's kind of that kind of three-pronged approach. In lab tomorrow, you guys are going to knock out some cooling curves. So I'll have test tubes for you. In one test tube will be pure, I remember it's naphthalene. Maybe it's the mothballs, naphthalene. But anyways, it's pure. You're going to see the temperature it freezes at. And then when I add a solute, or when I'm going to give you a test tube that's already had solute added to it, you're going to see it freezes at a different temperature. So it's going to be freezing point depression. So you're going to be coming up with that. Okay, so we're going to use this equation to come up with the molality of the solute. So I would rearrange this and say that the molality of the solute is equal. It's coming in a minute. But we're going to use the elevation of the boiling point temperatures, which is the T minus T naught. My builds are kind of throwing me off. So the temperature the elevated temperature we saw benzene boil at was 82.0 degrees Celsius. Literature said it should be 80.1 degrees Celsius if it's pure benzene. So since we're subtracting the round according to decimals, so our delta T Vp is 1.9 degrees Celsius. This is what I started to say. I would rearrange this to solve for molality. And there it is. If I rearrange my boiling point elevation equation, I have the molality of solute is equal to the delta TVP divided by KVP. Boiling point elevation divided by the boiling point elevation constant. So plugging in, this little anticlimactic, we put our 1.9 degrees Celsius, always use units even for plugging and chugging here. 1.9 degrees Celsius in the top. The boiling point elevation constant is 2.53, and units of these elevation or pressure constants are degrees Celsius per molal. So our units of degrees Celsius cancel. We have units of molal in the denominator of the denominator, and that actually then gives us units of molal. We round to two significant figures, and I get 0.75 molal. Again, I don't care what the solute is, it's a colligative property. So now we're going to change our temperature. We're going to change our, we're going to hone in now on not the boiling point elevation, the freezing point depression. So this is the equation for the freezing point depression. Now we know the molality, and of course we have the freezing point depression constant, okay? So it looks like this. The absolute value of the freezing point depression, the delta TFP, absolute value of, is equal to the KFP, which is 5.12 degrees Celsius per molal, times the molality, which we found from the boiling point elevation is 0.75 molal. It's funny how in my slides as I do this, I'm writing out molal. If you do a little m, that will work too. So units of molal cancel, and we have units of degrees Celsius, which is perfect. 2 sig figs, I get a delta TFP, absolute value of, is 3.8 degrees Celsius. Now this is where, in the bottom there, I said we just need to keep our wits about us, and remember it's freezing point depression. So we need to apply that 3.8 to the freezing point that pure benzene freezes at. So we're going to, subtract 3.8 units. So it looks like this. What it usually freezes at in its pure state is 5.5 degrees Celsius. And notice since I'm subtracting here, I went ahead and in parentheses, I put the units outside the parentheses. That's legit. So 5.5 degrees Celsius is what it usually freezes at. It's going to be depressed 3.8 degrees, so we're going to subtract 3.8 degrees. Round to 1 decimal. and you get now 1.7 degrees Celsius. So that's it. Come full circle. It works. Let's do another one. Yay! All right. It looks like this. I think I'll go ahead and draw a little picture up here. Because if I was doing this for homework, I would probably draw a picture. It's a classic. Oh, roll your eyes. A solution of lauryl alcohol. Now, sometimes in this sort of case, if you read it a few times, I'm going to go ahead and do LA is equal to my lauryl alcohol because I don't want to write lauryl alcohol everywhere. Okay, it's up to you. Oops, I spelled laurel wrong. Okay. I didn't spell alcohol. Okay. That actually, if you read it a few times, yeah, this is going to be my solute. And it says that I am going to add 5.00 grams of LA. Now I know it's my solute because notice the other thing I have is benzene, and it's not 5 grams, it's like 100 grams, right? 0.1 kilogram. So that's a lesser amount. I'm going to add it to benzene. Benzene, we'll just call it benzene. So I have 0.100 kilograms of benzene. And it says that, and we can look up benzene. So benzene is my solvent. And we can look up the different things about benzene, the freezing point depression constant, the boiling point elevation constant, the temperature at which it freezes and which it boils. It tells me that what the depressed freezing point temperature, so I'm going to go ahead and say T, not T naught, is 4.1 degrees Celsius. Okay. What is the molar mass? Now I'm going to put a question mark over here of lauryl alcohol. Question mark. Molar mass of lauryl alcohol. So mmLA. So my units are going to be moles of LA per gram. All right. Oh. My units are going to be grams of LA per mole of LA. Oh my gosh, today in physical science, we're just dabbling in chemistry in that class, and I totally butchered electron configuration. Oh, I should have my chemistry license taken away from me. Molar mass, grams per mole, so that's what we're after. Let's see how this works. Well, benzene, we know we can come up with freezing point depression constant. We got that. We know that we can come up with the temperature above this, which it normally freezes. And here they are again. That looks kind of familiar. So we can use the relationship between the depressed freezing point that we see and the freezing point constant for benzene to come up with the molality of the solute. And honestly, that's the key. We're trying to find the molar mass of lauryl alcohol, and if we know the molality in the solution, we can get there. So the molality of lauryl alcohol will be equal to the freezing point depression divided by the freezing point constant. So the freezing point depression, absolute value up, looks like this. We take the absolute value of that 4.1 degrees Celsius minus what it should freeze at, 5.53 degrees Celsius. So that will give us a positive 1.4 degrees Celsius. So that 1.4 degrees Celsius is going to go in the numerator over our freezing point depression constant to get our molality. So here's what that looks like. The molality then of the lauryl alcohol is 1.4 degrees Celsius, which is our delta T FP, divided by 5.12 degrees Celsius per molal, which was our freezing point depression constant. So units of degrees Celsius cancel. We're left with units of molal in the denominator, which is units of molal. Round to 2 sig figs, we get a molality of 0.27 molal. In Chem 1, I really, we ran into problems, and Chem 2 too, that we have to unpack. You can't, in order to finish this problem, we have to say, what does 0.27 molal mean? What 0.27 molal means is 0.27 moles of lauryl alcohol in 1 kilogram of benzene, right? It's moles per kilogram of solvent. So we're getting close. So if our goal is to come up with grams of lauryl alcohol per mole of alcohol, grams of lauryl alcohol per mole of lauryl alcohol, that was right. We can actually use this as our benefit, and here's what this looks like. Let's see, like this. 0.27 moles, 0.27 moles of lauryl alcohol. Like all the exclamation points. It's going to be about making sure you keep the units with the information you have and keep your eye on the prize of where you're trying to get to. In the problem, we said that we have 0.100 kilograms of benzene. From the molality, we came up with this. That there's 0.27 moles of lauryl alcohol in 1 kilogram of benzene. Well, I can go ahead and have kilograms of benzene cancel, and this is, I can get moles of lauryl alcohol that must have been in there then. So the moles of lauryl alcohol was 0.027 moles. I want to turn your attention, this is where a picture helps, I think. Do you see that that was the moles in 5.00 grams? So to finish up, all we got to do, and we're going for grams per mole, is to simply take that mass, 5.00 grams, and divide it by that 0.027 moles of lauryl alcohol, grams per mole. That's it. I can't guarantee there'll be one of these on the test, but I think, is this right? I have to double check the lab because you're doing tomorrow, but I think you guys might be having to do this sort of calculation. So rounding to 2 sig figs, we get 180 grams of LA per mole of LA. So that would mean that the molar mass of lauryl alcohol is 180 grams per mole. That bumps us up against another homework. Oh, did I pick up your homework yet?
No.
Oh, okay. Let me pick up their homework. Is their homework due? I got stuff graded. And I apologize. Every once in a while, I do seem to be leaving early. So if that's the case, just let me know, and we'll make it work. Still have here. Labs. And I'll double check on the equation sheet. Okay, that's it. We'll see you tomorrow.
Since we have nothing from this year.
So I don't know the lab number. What lab number is it?
430 was it?
But it's boiling point, it's freezing point depression, whatever that one is. So. That's okay, Sierra.